The distribution of prime numbers forms the strictly deterministic bedrock of arithmetic. A number is either prime or it is not, governed by rigid, immutable mathematical rules. Look at this simulation of an erratic random walk. When rapidly scaling to massive datasets, the sequence of prime numbers flawlessly mirrors pure stochastic randomness. This plot maps the Riemann zeta function. By calculating the distribution of primes along the critical line, where the real part is exactly 1/2, the function generates this blue and white geometric spiral, crossing zero at highly specific intervals. In 2001, mathematicians Philippe Bion, Jim Pittman, and Mark Yor published a paper that formalized the connection between these two seemingly incompatible systems. They established a core equivalence. The statistical properties defining random Brownian paths are mathematically homologous to the analytical properties defining the Riemann zeta function. The specific mathematical target of this equivalence is the Riemann z function. The z function is the completed, symmetrically balanced form of the zeta function. By mapping the z function directly to a probability density, the BPY synthesis transforms the proof of the Riemann hypothesis from a problem of infinite geometric zero distribution into a measurable problem in probability theory. This diagram shows a Brownian bridge, a continuous time stochastic process pinned to start and return to zero at a fixed time t. If we measure the total vertical spread between the highest and lowest points of this path, we isolate a specific random variable, y. The probability density of this range y is strictly governed by the Kuiper distribution. This is a statistical metric traditionally used to test whether a given set of data points is uniformly distributed across a circular domain. To integrate this probability density, mathematicians use the Mellin transform. The Mellin transform is an integral operation that converts a function's scale behavior into a continuous spectrum of complex frequencies. When we apply the Mellin transform to the Kuiper distribution of our Brownian range, the expected value of y to the power of s minus 1 yields exactly 2 xi of s. The mathematical roots of this xi function correspond exactly to the non-trivial zeros of the Riemann zeta function. Identifying this exact stochastic equivalent provides a new, fully quantified vector. Mathematicians can now attack the Riemann hypothesis using the established, testable laws of probability theory. The BPY equivalence relies on the Jacobi theta function, a specific power series that links the discrete properties of integers to continuous analytic functions. The Jacobi theta function serves as the fundamental solution to the heat equation. The heat equation is a parabolic partial differential equation that determines how temperature variations within a specific region smooth out over time. Look at this simulation of thermal energy diffusing outward. The heat equation physically describes this diffusion of particles, the precise mechanical driver of Brownian motion. Riemann's original integral for the xi function explicitly contains the theta function. Therefore, the physical dynamics of thermal diffusion are hardwired directly into the analytical structure of the prime numbers. Jacobi theta functions possess unique topological properties. They are doubly periodic, meaning their values repeat systematically in two distinct directions across a lattice in the complex plane. This 3D torus visualizes that double periodicity. Because the function repeats in two directions, mapping its phase changes naturally forms a torus, with the continuous color spectrum tracking the mathematical shifts over the complex lattice. This lattice structure connects directly to the work of Srinivasa Ramanujan, who studied the modular properties of these functions. Ramanujan used the arithmetic of these lattices to identify Heegner numbers, like 163, which allowed him to calculate almost integer values of extraordinary precision. The specific topologies formed by the Riemann zeta function are not arbitrary logical artifacts. They are strictly mandated by the physical rules of thermodynamic diffusion. In 1997, mathematician Xianjun Li published a new, distinct criterion for evaluating the Riemann hypothesis. Li's criterion hinges on a strict requirement. A specific sequence of coefficients, denoted as lambda sub n, must be strictly positive for all values of n. To calculate those coefficients, a Mobius transformation physically wraps the vertical critical line onto a unit circle. The zeta zeros project radially outward from the boundary, like sharp rays. Notice the structural compression. Approaching coordinate z equals 1, these radial structures pack infinitely close together. This purely geometric construction maps directly back to the BPY probability synthesis. BPY proved that Lee's coefficients are mathematically identical to the cumulants of the random variable L, defined as the natural logarithm of 1 over our Brownian range Y. Cumulants are a set of quantities that provide an alternative to traditional statistical moments for describing the shape of a probability distribution. Current numerical studies empirically confirm that these coefficients remain strictly positive, even when calculated at extremely high values of n. When we analyze the sequence of these coefficients, we see a smooth upward growth trend, overlaid with microscopic structural oscillations. If the Riemann hypothesis were false, these microscopic oscillations would eventually destabilize, exponentially exploding into negative values at large scales. By translating infinite, untestable geometric zeros into a sequence of stochastic cumulants, mathematicians have established the most viable quantitative path to proving the Riemann hypothesis. Proving the Riemann hypothesis now relies on demonstrating that the random variable y belongs to a specific mathematical class of infinitely divisible probability distributions. This stochastic architecture manifests in theoretical physics, specifically in the study of chaotic quantum systems. The distribution distances between the zeta zeros perfectly model the energy levels of chaotic quantum systems. This statistical behavior is known as the Gaussian unitary ensemble, a mathematical model used to describe the properties of quantum systems exhibiting chaotic dynamics. We also see the BPY probability laws utilized in modern financial mathematics. The exact stochastic functionals developed to map the zeta function are now deployed to compute spot volatility within massive sets of high-frequency trading data. The mathematical roughness that defines the distribution of prime numbers has a formal equivalent in the macroscopic dynamics and volatility of global market movements. This reveals a strict underlying unity between pure mathematical logic and the mechanics of the physical world. Prime numbers form the indivisible foundation of arithmetic, yet their distribution is dictated by the exact same statistical laws that govern the chaotic dance of a single dust particle suspended in fluid.